Hello? Hello?
Sir, just now he joined, sir. Yeah. Sir joined.
So shall we start? Sir, shall we start?
We can start, but you have to allow me to share my slides.
Yes, sir. We'll share the screen after the introduction.
Okay.
Okay.
There's a disturbance. I don't know why.
Now it's okay. Now is it okay?
Yeah, it is okay now.
Yes, sir. Welcome participants for the second session of this second presentation of this session today morning. I am happy to introduce Professor Suddhasatwa Basu, Director, CSIR-Indian Minerals and Materials Technology, Bhubaneswar. He has 28 years of teaching experience since 1994. He is a professor from the Department of Chemical Engineering, IIT Delhi. His areas of interest include electrochemical, photoelectrochemical phenomenon, fuel cells, wastewater treatment, enhanced oil recovery, and detergency. He has received many awards. Among them, few are he has received the prestigious DAD Faculty Researcher Award on Fuel Technology from the University of Karlsruhe, Germany in 2006. Awarded the Query Award by the British Council. He received a Fellow of Institution of Engineers in 2011. He is also a recipient of Fellow of Indian Chemical Society 2012. He has received Isaac Journal Publication Award in the year 2012. First prize publication peer-reviewed international journal, and he has also received the Best Paper Award in the International Conference on Electrochemical Society of India, which was conducted in Earnest in ICE Bangalore, August 2014. He is an expert in the area of fuel cells, and he has completed many projects, national and international projects. We are happy to welcome you, sir. We would like to attend your presentation expert lecture. That is on introduction to solid oxide fuel cell. Over to Professor Basu. Bhaskar, share the presentation.
Myself.
Yes, sir. Yes,
okay.
sir. Yes,
so
sir.
I could unmute myself. So good morning to all of you, all the participants. Thank you, Professor Murugan and Professor Biswas, Director of NIT Rourkela, and Professor Murugan from Professor at NIT Rourkela, for inviting me, who is the convener or the coordinator of this faculty development program sponsored by the ICT. And I think it's a very good initiative, as I said in the inaugural inauguration of the program. And I'm sure after that, now about 2 days are over, and I'm sure you have benefited well from the different speakers that was listed throughout the program, and there are more speakers are coming or will be there throughout this week. And I have decided, although we work in the area of broadly in fuel cells or PEM fuel cells and direct ethanol fuel cell, direct glucose fuel cell, all these things are developed about 20 years back. Now they're in commercial stage in many of them, like ethanol fuel cell is commercialized. Hydrogen fuel cell, of course, developed by long back. And we worked also on that, different aspects like degradation mechanisms and how you can revive a fuel cell. All those things we have worked on PEM, and then solid oxide fuel cell as well. So that is the topic that I have chosen for today's introduction of the solid oxide fuel cell. I understand there will be followed by my talk in coming up days. There will be one more talk on solid oxide fuel cell, which will be more into the materials and intricacies of the solid oxide fuel cell material and the functional layer and the anode cathode development of different type of anode cathode development and things like that. So I thought that if we give an introduction here, then that will be very apt from my part. If I give an introduction from on the solid oxide fuel cell. So I'm currently now sharing my slide. Just confirm me whether you're able to see my slides, and then I can start formal presentation. Are you able to see my slides?
Yeah, visible.
Yeah. So currently I am the director of Council of Scientific Industrial Research, a lab in Bhubaneswar used to be called Regional Research Lab. Now it is called Institute of Minerals and Materials Technology. So I'm currently the director of this lab, and I'm speaking from there. But most of the work developed or the work is done is in IIT Delhi, where I'm the professor of the Department of Chemical Engineering, and from where I came to IMMT Bhubaneswar to lead this lab. In this lab as well, the work on solid oxide fuel cell is going on. In the material chemistry division, they developed, because this lab is also develops not only minerals and extraction, but also it does material development. So the material chemistry division, there's a lot of work goes on material development for Srfc. So with this brief introduction, but primarily my work is done at the IIT Delhi. And what I'm going to talk about is what is solid oxide fuel cell. Of course, we will skip the polymer electrolyte fuel cell, which has been covered by Dr. Rajalakshmi, I understand, on the first day. And then I would mostly, as you see, that different components of SFC, configuration, degradation, low temperature SFCs, and hydrocarbon SFCs that I'm talk about. So the concepts started, although the PEM fuel cell, as I said, those who were there in my inaugural talk, 1839 by William Grove on development of hydrogen-oxygen fuel cell, not a PEM fuel cell, and then later after the World War, the proton exchange membrane developed, and then PMFC was developed, as I mentioned. But the work on SOFC started much late. And the first thing is done by Walter Nernst. For Nernst equation, you must be knowing it. And he was working on development of filament for glowing, which is also done by Thomas Alva Edison, that tungsten bulb. So at that time, people were working on a light-emitting material, so that instead of using lamp, the flame that we use, the diya or deep, whether one can have a electrical bulb. So that development was going on. In that context, they were trying to come up with a material which will glow under potential difference. So the Nernst patented a material with a 85% zirconium and 15% yttrium, yttrium oxide and zirconium oxide. And it did glow and called electrical glow light. This was an 1899 patent and 1897 work. So what it shows that the conductivity of pure oxide rise very slowly with the increasing temperature. So that's the starting point of solid oxide development. or solid oxide fuel cell. And there's a great work done in Siemens Westinghouse in 1960s and 70s in the range of a kilowatt to about 100 kilowatt range of solid oxide fuel cell development, mainly by Subhas Singhal, who is the Indian origin American, working in PNNL in US. And with Westinghouse, they developed that and demonstrated it in late 1970s and beginning of 80s of the 100 kilowatt solid oxide fuel cell. So let me go a little further that with the knowledge that NERST created, of course, the intention was something different, that glow light to create a lamp, but that was found that if you have a zirconia and yttria together, there is a huge increase in conductivity at the high temperature. So essentially, with that cue, there was further development has taken place in Siemens Westinghouse and in PNNL and many other labs in Japan as well as in US primarily. And they thought that with the use of solid oxide as an electrolyte, completely a solid material, and hydrogen oxide, one can make the solid oxide fuel cell. So again, here also like PEM fuel cell, it's about the hydrogen and oxygens are the fuel and the oxidant that is sent to the anode side and the cathode side. You can see that I have an anode where hydrogen is being pushed. I have a cathode where oxygen is being pushed. Now, in between you have electrolyte, which is what is called yttria stabilized zirconia, something which is here, yttria stabilized zirconia. So yttria is being put in the zirconia. Mostly you have zirconia, and all of them are very cheap, abundantly available, and they conduct oxide ions at high temperature. So that is how it works. It has got an anode, which is generally a nickel cermet, and then there is a cathode, which is like a oxide material, transitional metal oxides material, and they convert oxygen into oxide ion. That oxide ion at high temperature moves from the cathode side to the anode side, combined with hydrogen, produce water. In the process, electrons are generated, and that is how the solid oxide fuel cell works. But it has to have a temperature about 800 to 1000 degrees Celsius to have a very high conductivity of oxide ion in the electrolyte. Without the conductivity of these ions, obviously this will not work. And you can see that the temperature is 1000 degrees Celsius. So where this temperature will be coming from? Then you are creating energy and you are spending energy. It makes no sense. But fortunately, this process is an exothermic process and it generates heats on its own. So what you need to do is that initially you have to actually add energy in the form of heat to achieve the temperature of 800 degrees Celsius. But since these reactions are exothermic in nature, it will maintain its temperature. Not only that, it will rise. So you have to take away heat to maintain its temperature within 900 or 1000 degrees Celsius or 800 degrees Celsius. Otherwise, no, it will actually degrade because they keep on rising the temperature. Because at the high temperature, one of the advantage you have over the PEM fuel cell is the kinetics of hydrogen oxidation or oxygen reduction that is taking place at the cathode anode is be tremendously high, because those who are having background of chemistry, chemical engineering and mechanical engineering, you must have learned in your class 12 that with the increase in temperature, the kinetics, the rate of reaction increases. That's a simple thing. How my slide got unshared? I'm seeing something else now. Can anybody? I'm seeing Srinivas Prasad Sanaka instead of my slide. Can anybody help me in this? I do not see my slide. I see Mr. Sanaka.
Sir, we are seeing your slide only, so solid oxide fuel cells.
But I am seeing Mr. Sanaka. Mr. Sanaka, can you turn off your video? We don't require it your video. I won't be able to use. I won't be able to point out my slides. Is it not? If I cannot see my slides. On my slide, Mr. Sanaka's frame is coming. Somebody needs to fix this.
Sanaka.
Mr. Sanaka, can you put your video off? Kindly. If you do not know how to do it, please log out. Otherwise, how do I change my slide? How do I print my slide? You have to understand that. Those who are organizer. Mr. Srinivas Prasad Sanaka.
Sir, wait, sir, I am checking, sir. Mr. Srinivas.
Kindly log out from Microsoft Teams and log in again. I cannot, it is, the frame is put in front of me. Yeah, he's leaving. Thank you very much. But still, there is some problem. I can't see it. All the people, those who are attending, their frame is coming. So somebody needs to fix the frame. Do you know the operator in Microsoft, those who have created the account, they can put a frame that will be highlighted. Currently, everybody is highlighted. My PowerPoint slide is not highlighted. Please call your IT person and please fix it. I'm seeing those who are attending. There are about frames. You can select a frame which is to be highlighted. So currently the frame highlighted is those who are attending, not the person who is speaking. Unless you fix that.
Sir, we have fixed the issue, sir. Right now, we are able to see your slide only, sir, your presentation only.
I can't see my slide. I cannot do anything. You can see my slide, but I cannot see my slide now. I'm unsharing and sharing again.
Yes, sir. Yes, sir. Okay, sir.
Can you see my slide?
Yes, sir. Yes, sir.
Okay.
Yes.
So, Sanaka, can you log in now? I asked you to log out. Please log in. You must be one of the participants. So there must be a problem in somewhere we don't know. Mr. Sanaka, please log in. Okay, so I'll continue. So I was here and then I was talking about that it's an exothermic reaction, and that is how the temperature is maintained. Once we increase the temperature, start the process. Okay. So the cell reaction that takes place in the anode and cathode is given here. If you remember, my anode is here and my cathode is here, and this is the electrolyte. So anode, obviously, I said that it will react with oxide ion, which is generated at the cathode from oxygen taking 2 electrons, which is coming back from here. It becomes an oxide. Then oxide transferred through. Just I want all of you to concentrate, because we must be having some chemistry background, but there are mechanical engineers who are also attending. It's a simple reaction that oxygen taking 2 electrons and giving oxide ion. So that reaction is taking place at the cathode. So oxide ions are forming, and then it is able to pass through the electrolyte. It allows oxide ion to pass through, and the electrons come from the outer circuit from here. Now, how electron comes, I'll come back because I'm starting from the back side. Then this oxide ion then goes to the anode side. We are giving hydrogen, it forming water and giving 2 electrons. So I'm going back again. So this oxide ion then combines with hydrogen, giving water and 2 electrons, which is coming out from here. And this is the electrical load or electrical work that is done by the system. And after that, the electron comes back to cathode. So that is how electrons are generated and electrons are consumed. And in between, you have a load, which will obviously, like your light, fan, or whatever, it has got a resistance, and electrical energy is being generated and consumed. So that is how this fuel cell works. But one thing I want to point out, I just gave a hydrogen and oxygen as a fuel and an oxidant. What I've shown also the methane as a fuel. So even if we have a methane as a fuel, which can go, it's not the hydrogen and methane together. It's a hydrogen is separate and methane is a separate. So I can use hydrogen or I can use methane as a fuel, and it combines with oxygen, and a similar reaction taking place to generate electrons. But there is, of course, no balance. So balance can be created. So overall reaction, if you see the first one, hydrogen and half oxygen give you water. And you can find out from the Nernst equation, and using the partial pressures of the hydrogen, oxygen, and water, specifically moisture, because you have high temperature, that what is the E or EMF of the cell, which can come up from the Nernst equation. Similarly, I can balance it with CH4 2H2O2 to give you 2H2 and CO2 when I combine these two with reaction at the anode and cathode to get that. So as I said, that now I'm coming back to the material. I have just told you the basic principle how a solid oxide fuel cell works. But what are the material that we have? And why yttria stabilized zirconia is oxide ion conducting? So yttria stabilized zirconia is actually shown you here, that yttria is used as a dopant in the cubic structure of zirconia. But there is a mismatch of valency of Y, the yttrium, and Z, the ZR, the zirconium, class 3 and class 4. Because of the difference in the valency, and it has to be neutral or electrically neutral or electrochemically neutral, so they have to share the oxygen, because you are actually adding zirconia to yttria or zirconium oxide to yttrium oxide. There's a mismatch in valency Y3 plus and ZR4 plus, and some oxygen to be shared in this cubic structure such that it is electrically neutral, and that creates a vacancy which is shown you here. So because of the mismatch in valency, there will be a vacancy of oxygen created, and that vacancy moves from one crystal lattice or one crystal to another crystal, how the oxide ion actually able to transport or transfer or conduct through yttria stabilized zirconia electrolyte at high temperature. In normal condition, this will not move because it has got an activation energy to be overcome. So when you increase the temperature, it gets excited, and the vacancy can move, and in other words, vacancies also means oxide ion movement. That also moves, and that is how the oxide ion conductivity is there in yttria stabilized zirconia electrolyte, which is used in solid oxide fuel cell. And generally, this kind of notations are used, Kruger-Van diagram or notations, to show that how zirconia and yttria together to give you a vacancy and how oxide ion conductivity is there. Okay, when ZrO4 and Y2O3 are mixed together in a very small amount of more than 7 mole% of Y2O3, or I should have 15% of Y2O3 and 85% of ZrO2, zirconia. So that is the reason why this works. One point I want to highlight here at the fourth is its conductivity. By this time, you are exposed to conductivity, especially in the PREM fuel cell, proton exchange membrane fuel cell. And I can see conductivity is very, very high, 0.1 Siemens per centimeter at about 800 degrees Celsius, which is a strongly high. Plus, you have 800 degrees Celsius is maintained because of the exothermic reaction. The kinetics is very, very high, and you generate a lot of electron in a given time. If you generate a lot of electrons because of the high rate of reaction, then obviously you get a lot of current. So here we are showing you the ionic conductivity of such kind of material. I gave you in details about yttria stabilized zirconia, and henceforth we write it in short, YSZ. There are other material similarly like Samaria doped ceria, SDC, or gadolinium doped ceria, GDC, or you have LSGM, lanthanum strontium gallium doped manganite. So, and you have bismuth vanadium oxide, bismuth copper vanadium oxide. So all these material are potential electrolyte for solid oxide fuel cell. And you can see this is 1000 by T plot. So if I take 1000 degrees Celsius, the yttria stabilized zirconia would have about 0.01 Siemens per centimeter, but it can about rise to about close to 0.1 Siemens per centimeter. Okay, little higher temperature. And the best one is SDC at low temperature, like at 800 degrees Celsius, where this gives about more than 0.01, little more than 0.01, but SDC gives close to 0.1. Even bismuth vanadate or bismuth copper vanadate, even better at 700, gives even more than 0.1 Siemens per centimeter. And I think by this time you are exposed to the units of ionic conductivity or conductivity Siemens per centimeter. And this is of course temperature. We have plotted 1 by T in terms of Kelvin. Okay. So these are the prospective electrolyte, and YSZ of course is most suitably used because it's a very stable, it doesn't degrade, cheap compared to bismuth copper vanadate or vanadium oxide, where it's unstable. And that is how, even though it has got a high conductivity at low temperature, it is not being used, although it has a potential to use it. But what is the other material used is SDC and GDC, Samaria doped ceria and gadolinium doped ceria, which we put it in a intermediate temperature solid oxide fuel cell operating about 700 degrees Celsius. So what is the criteria for development of different kind of material? One is ceria based, I talked about, zirconia based, I talked about lanthanum and bismuth based, I talked about. So this is the attribute or the property a electrolyte material should have. Okay. And you could see that it should be stable, it should be highly conductive, so excellent stability, oxidizing and reducing environment. Because if you remember, if I go back to my structure, this is an electrolyte, this is an oxidizing environment, and this is a reducing environment. This is a reducing environment, and this is an oxidizing environment. And in this environment, this should be stable. The electrolyte should be stable. And that is how zirconia based YSZ, 3 YSZ is. 3 means 3% of Y in Z, or zirconium oxide. Good compatibility with a cathode material. Next to it is a cathode material. Okay. And then lanthanum base also good, high conductivity, and so forth. Low ionic conductivity compared to them, But thermodynamic instability in reducing atmosphere is a problem with the bismuth oxide. That is what I was talking about, that it's not a stable. Okay, although it's a low conductivity, but it is quite stable here. In the case of GDC as well as YSZ. So, as I said, zirconia base is 8 YSC, 3 YSC, 8 means 8% yttria, 3% yttria. This is scandium stabilized zirconia, calcium stabilized zirconia. This is Helia based GDC, SDC I talked about, gadolinium, samarium, yttrium, and so on and so forth. Lanthanum based LSGM I talked about, manganate, gallium, strontium, lanthanum, doped. Okay, bismuth oxide I talked about, and some pyrochlores and barium, brown millerites also is there. So now I want to talk a little more on the cathode and anode. So cathode is used as a LSM, which is lanthanum, strontium, manganate, which is a material which can be made from lanthanum oxide, strontium oxide, and manganese oxide. And this kind of material is a very good material for oxygen reduction reaction, which is taking place at the cathode. And it has got a very good conductivity and require about porosity to reach oxygen to reach in cathode. Because one thing important which I want to show you here is that this material needs to be porous in nature, this material as well. Because you do not want to only have a reaction at the surface, but you want to have a reaction everywhere. So oxygen needs to reach every corner here. So then it has to be a porous in nature. So that is how it has got a porosity of 40%, very good conductivity, because you required oxide ion generated and conducted into the electrolyte. That has to take place from the cathode to the electrolyte material and further to the anode. Then you're operating at a high temperature. The thermal expansion coefficient, TEC, all these three materials which are sandwiched together, anode, electrolyte, and cathode, should have a similar thermal expansion coefficient, TEC. If it doesn't, then at a high temperature, there will be crack formation, because each one of them will expand in its own way. And if there's a mismatch of expansion of coefficient, then obviously there will be delamination and there will be breaking of the cell. And it does take place. That's a big problem. Those who are trying to go into Srfc research, and it's an art to have a right mixture of binders and solvent and the pore former, so that you get such kind of consistency that when you laminate each layer onto others and then you sinter it at high temperature, there is no mismatch in thermal expansion coefficient and there is no delamination of the layers, because you have three layers: anode, cathode, and electrolyte. I mean, in between anode and cathode, you have electrolyte. So thermal expansion coefficients are shown for all of them, and dimension can be there, which is like shown you here, which is kind of matching. And electrolyte I only talked about that this is 8 YSZ, about 0.08 in 0.92, 8% in zirconia, and so we say call it YSZ in short. Yttria stabilized zirconia. This is lanthanum, strontium, manganate, so LSM and YSC. So now onwards, I will little bit use acronym so that it is easy to go forward. And porosity in the electrolyte should not be there, because you do not want. I'm going back here. You do not want that this is a porous. This is a porous structure because oxygen has to go to every part so that there is a reaction taking place in whole bulk. Similarly, anode also. But you do not want this to be porous. You do not want oxygen to pass through the electrolyte, come to hydrogen side, or hydrogen to pass through, come to the oxygen side. It has to be perfectly sealed, so it should be a dense electrolyte, but it only conducts oxide ion in the from the right to the left. So that is why it is nil porosity, and permeability should be 0. Ionic conductivity I talked about. TEC is almost like matching in the ballpark figure. Film thickness should be as small as possible, so that there is no resistance, or there is ohmic resistance is as low as possible. Now I come to the anode material, which is a nickel YSG cermet. We need to put YSG because nickel is a material which can conduct electrons, but it cannot conduct oxide ion. Because if I again frequently go back to my diagram here, if you remember that this oxide ion has to come to the anode, and there should be conductivity of oxide ion every part, so that there is a reaction taking place between oxide ion and hydrogen to form water and electron, which is this reaction, right? And that to happen, this material also need to be oxide conductor, and as well as electron conductor. If this is not an electron conductor, then electron generator needs to be taken out. So a reaction taking place here with the oxide conductivity and hydrogen coming in because of the porous structure, the electron generator has to pass through this and come out. So it has to be electron conductor as well as oxide ion conductor. The LSM that I talked about as a cathode is a mixed ionic electronic conductor. So same material which can have an ionic conductor and as well as electronic conductor. But in the case of anode, nickel is used as a catalyst. It has obviously, you know, nickel is a good electronic conductor, but not at all oxide ion conductor. All metals will not conduct any oxide ion. It will be a good conductor of electrons. So what we do, we actually mix NiYSG, and that is how it's called cermet. Ceramic material with metal. The ceramic material is my zirconia or yttria stabila zirconia with metal, nickel. We call it now cermet because it's a mixture of ceramic and metal. And nickel is about 60% to 65% by weight, and 30-35% or 40 or 35% is YSG, which provides its work is to just to provide oxide ion conductivity so that the hydrogen oxidation reaction can take place. So hydrogen with oxide ion can form water and give away 2 electrons, which goes to the outer side. Again, you can see thermal expansion coefficient is the same ballpark figure as electrolyte and cathode. Okay, conductivity of electrons are very, very high in nickel. Okay, which is 1000 or 1500 Siemens per centimeter. YSG conductivity of oxide ion I already talked about. Porosity again should be 40% because you want the reaction to take place not on the surface but in the bulk, which is a layer, thin layer, but still it has got a porosity so that hydrogen can reach everywhere through the pores. And then you have an interconnect. Why we require interconnect? I can go back to the structure again. Because you have a one cell, but you require many cells. And so the material that comes here called interconnect. So this interconnects with this cell and the next cell and so on and so forth. So you can put many cells in series and parallel. So that is called interconnect. And that has to be also a very important material to be think of, which will be conducting electrons if it's on a series connection. So one of the interconnects is shown you here. Lanthanum, magnesium, chromium oxide, and it has got a very high conductivity, same thermal expansion coefficient. Of course, dimension you just as you want to make it. So requirement of cathode is high electronic conductivity, chemically compatibility with the cell component, usually electrolyte, which is YSG, should be porous, stable in oxidizing environment because oxygen is coming at the cathode going and becoming oxide ion. Large triple phase boundary, as I said, that it has to be porous. Triple phase boundary means one is solid, another is another is gas, So that is how the triple phase boundaries are coming into picture, where we have generally two material. One is oxide ion conductor, another is a ionic conductor, electronic conductor. Other phase is just air. I mean, I would say oxygen. So that good high amount of triple phase boundary created if you have a good porosity. Catalyze the dissociation of oxygen. Oxygen become oxide. Addition with the surface of the electrolyte. Thermal expansion coefficient should match with the Srfc material. Requirement of anode, electrically conductive nickel, as an example I showed, highly electrocatalytic activity, hydrogen combined with oxide ion to give water and electrons. Triple phase boundary again should be there because you want a bulk reaction, stable in reducing atmosphere, hydrogen atmosphere, so it's a reducing atmosphere, it should be stable material. Can be made of thin enough to avoid mass transfer losses. It shouldn't be having mass transfer resistance because hydrogen has to reach very easily to the site of the reaction. Thermal expansion coefficient should match. Chemical compatibility with the nearest component, whether it's a interconnect for the next cell connection, because you want to put many cells together in a series, and also with the YSZ, fine particles, so it will give you high surface area, able to provide direct internal reforming if required. That is in the case of methane, if you want to have an internal reforming which makes hydrogen, and that hydrogen goes through oxidation reaction. So requirement for interconnect is stable under high temperature, oxidizing and reducing environment. Because when you put them in a series, okay, I'm going back again. If you put them in a series, so one side this is anode, the next side it is cathode. So it has got a anode, cathode, because you cannot put anode, cathode, right? If it's a series, anode, cathode, or positive, negative. So that is how in both the atmosphere, the interconnect should be stable at high temperature, both oxidizing and reducing. One side it is oxidizing, other side is reducing, because you are joining anode, cathode, or positive, negative electrodes. Because when you have a battery, you remember, you don't put the same pole or same polarity or positive together. You put positive, negative in a series. Very high electrical conductivity. This is the place where you take out the electrons. High density, no open porosity. So it should not, one side of the hydrogen should reach to other side of the oxygen. Strong high creep resistance, okay, because it's under pressure when you put them, all of them together. Good thermal conductivity, so that you can take away heat. Phase stability in temperature range, okay. Resistance to sulfur poisoning. There could be a sulfur in your fuel, trace amount, and that should not create a problem, especially when you are making hydrogen from the fossil fuel. Low materials and fabrication cost. So cost should not be high. So ceramic interconnect at high temperature SFC, like doped lanthanum chromides, doped yttrium chromides are known as interconnect. Metallic interconnect is Croffer steel or high chrome alloys, iron superalloys, nickel superalloys, ferritic steel, the high chrome steel that I talked about, Croffer steel, the high stainless steel which can go to high temperature. And critical issue is chromium evaporation. So we are using chromium, and that should not be happening here. Sealing, because you could understand, I will not go back to my previous slides to show you the picture. I will now come to the real picture of SFC. Because all of these material you are putting together in a sandwiched form. So from the sides, there could be leakage of hydrogen oxygen. So that has to be sealed, and it's a big challenge. It has to be a ceramic seal which can withstand temperature of 800 degrees Celsius. You have to see that how difficult. It's not that any sealant you can put. So you cannot put any polymer as a sealant. You cannot put any metal as a sealant because they all melt. So you can put ceramic sealant, which is cheap, and at the same time can withstand that temperature, and it will not break away, or no leakage of gas will take place, because that will create a havoc. So it should be electrically insulating. Sealant should not be conductor. Thermal expansion compatibility should be there with the cell component. Chemically, physically stable at high temperature, which is about 800 or 900 Celsius. Should be gas tight, no leakage of gas. Chemical compatibility with other components where we are putting the sealant. Provide high mechanical bond strength and low cost. Glass ceramic material is a strontium, lanthanum, aluminum, silicon oxides. All oxides are good sealant that shown in here in a composite form. And the sealant you required, this is of course I was talking about, because this is how a real cell would look like, and there are many cells together, a interconnect which is connecting one side of the anode to another side of the cathode. This is the interconnect I told you. Okay, so when you put them together, they are now separated. You have to press them together to put many of them. From the sides, there could be leakage, and to stop that leakage, we put the sealant. Just wanted to explain you about the importance of sealant material. Now coming to Srfc design, mostly I was talking about planar design, but now I talk both planar and tubular design and monolithic design. So tubular design is, although it has been put forward by Westinghouse when they come up with 100 kilowatt, 200 kilowatt Srfc cells in 1970s, but the planar design is most popular and being taken forward. It's the only Westinghouse technology and some other company data that used as a tubular design of anode, cathode, and electrolyte material, put them together. Otherwise, it's a planar design, which is very conventional, very easy, and but the sealant is not required in the case of a tubular design, and you can easily assemble, deassemble in the case of a planar design. So let us go a little detail into what a tubular design or planar design would look like. So first I'm talking about a tubular design, and you could make out that we have now put the anode, cathode, and electrolyte together in a tubular form. That means I have to extrude the cathode material, at the same time I have to sinter it, and then a tube is formed. On the tube I would put so I have a cathode tube, which is mostly taking the load or giving the strength, onto which I put a layer of electrolyte which is white. It's a kind of cylinder. Okay, so you can have an extrusion. You must have seen extrusion process. Those who have a polymer background, they know it very well. Otherwise, this is a very common instrument. It's mechanical engineers, chemical engineers, and polymer engineers would know that, by which you can make a kind of pipe. So extrusion, by extrusion way, you can make the cathode as a cathode tube. It's a hollow tube, onto which you can have a thin layer of coating, simply a paintbrush or coating of electrolyte, which is the white color, as I showed you here, by spray, by EVD, by coating, by dip coating, you can have that. But in the case of cathode, which actually taking the load is by extrusion principle. And then on the electrolyte, you have to put a thin layer of red color, which is your anode, which is again deep coating, screen printing on the tube that you already made, and cathode is giving the strength. And this is your interconnect. So there is another tube comes here, and they are connected. That tube is connected to another one in the top. Like that, you can have a series parallel connection between the tube by using this interconnect, which can connect cathode to cathode and anode to anode, or cathode anode in a opposite direction to give you a series or a parallel connection. So the bundle of tubes are put together, give you a stack in the case of tubular design. But the most popular is a planar design, and very easy to operate. Is you have anode, then you have an electrolyte, and then you have a cathode. You use tape casting process to cast it one into other. So if I take a cross-sectional view of this material of anode, electrolyte, and cathode, it will look like this. I have a porous anode, which is nickel YSZ. You can see it here. Then I have a very densely packed electrolyte. As I said, that electrolyte cannot pass oxygen or hydrogen from from one side to other side. It has to be densely packed, no porosity, oxide ion conductivity, and which is visible here, that is densely packed. Whereas cathode and anode is porous in nature. And this is cathode supported because cathode is very having high weight to give a good support to both the electrolyte and anode. But anode is also having porosity and quite a large width, so that all the hydrogen oxidation reaction can take place. And so these are put together. Then you have an interconnect. So that interconnect connects cell of the cathode to a cell of the anode in a series connection. So a positive electrode is connected to negative electrode, and one side of the interconnect will pass air because it's close to the cathode. The other side of the interconnect will pass hydrogen because if it is close to the anode of the next cell. And this process continues to give you a stack of 20 cells, 30 cells, so that each cell, when generate about 1 volt, you get 40 volt or 20 volt or 60 volt as you require. Okay, potential difference to be created, and then current passes. So this was the ACM of the cross section of the cathode, anode, and electrolyte, and this is the real picture of this cathode, anode, and electrolyte together. Okay, on a hold in hand. Sometimes it's called the green tape. Okay, because green color of anode. Okay, this is how it would look like, and many of them we will put between the interconnect, and that is how it works. So as I said, that it could be cathode supported when a cathode is large in thickness, which will take the load or they give the strength. It could be anode supported, where anode is in high width, thin electrolyte, and less thicker cathode, or vice versa, high electrolyte supported cell with a high electrolyte thickness, which supports the strength or gives the strength of the each cell, whether compressive or tensile. Okay, one thing you can understand, that electrolyte thickness increases, the resistance of the cell increase, because now oxide ion has to conduct from a larger distance because of the high thickness. But here the distance is small, here the distance is also small. So resistance, or the ohmic resistance, will be less in the case of anode supported and cathode supported compared to the electrolyte supported. So this is what the advantage, disadvantage of the different anode supported, cathode supported, electrolyte supported cell. Anode supported cell is very popular because hydrogen goes through oxidation reaction, which gives the electron. So if you have a larger width and porosity, more hydrogen can be converted. So this is the current status, although this is a little older, but there is not a big change so far taken place, the development that we had. So recent results of distinguished Srfc laboratories are shown you here. You can check that you can get about 2 watt per centimeter square at 800 degrees Celsius. Your PEM fuel cell or no other fuel cell can give you 2 watt per centimeter square of power in just 1 centimeter by 1 centimeter. In such a small cell, 2 watt will not give you. PEM fuel cell usually will give out a 1 watt. Okay. And then the stack power per volume also, 1 liter give 1 kilowatt, 1 kg give 1 kilowatt. Warm up is about 1 minute. It goes from 0 to 800 degrees Celsius, which is through external heating. And because it's an exothermic reaction, it remains at 800 degrees Celsius. Not only that, you have to take away heat because otherwise temperature will rise and rise and rise. Some of the points are shown you here. And the operating temperatures could vary. As I said, that there could be high temperature SOFC, low temperature SOFC, and intermediate temperature SOFC. So about 800 or 900 degree, I would say high temperature, 600 or 700 is an intermediate temperature, below 600, 550, 500 is a low temperature SOFC. And all this work is going on, and there is a lot of improvement. You can see 2 kilowatt per liter or 2 kilowatt per kg, which has been improved from 1 kilowatt by different methods. And then it has got a 5,000 hours of duty life. And one of the best company currently is developed is Bloom Energy. You must have heard. Bloom Energy is a company owned by a NRI in the US, and the Bloom Energy, because California state gives a lot of subsidy when you use green energy or you use hydrogen energy. So the Bloom, about 8 years back, started working with Microsoft, Google, many others to put at least part of the power requirement in their head office in San Jose. All these IT companies, big IT companies, eBay and such kind of companies, Amazon, their head office, their corporate office is partially actually lighted, or the power requirement comes from using SFC technology developed by Bloom Energy, which is owned by an Indian NRI. We have also office in Bangalore and as well as at Mumbai. There's some development they're doing here by using natural gas, or Indian natural gas, or LPG, liquefied petroleum gas, to use it in fuel cell. Methane, as I told you, can be used. So that is hard. So I just want to mention that nickel YSZ is used very well for hydrogen fuel cell. And at IIT, we work a lot on methane fuel cell, propane fuel cell, and butane fuel cell. But nickel, under this hydrocarbon at high temperature, goes through a coking process by which the carbon deposition takes place, and by which the cell becomes dead, and all the pores are clogged, and your fuel cannot reach out to the catalyst surface. So it's not suitable for hydrocarbon fuel. Hydrogen, of course, you know that cost is high, storage is a problem, hydrogen transportation is a problem. So that is how one look at it, that intermediate solution for use fuel cell is also hydrocarbon as a fuel, like methanol, ethanol, or methane, propane, butane, which is of course easily available, which we generally burn. Methane we burn, propane, butane we burn, so, and we get thermal energy out of it. So I just showed you here that how cells in the lab scale, how cells are generated just by tape casting process. The bigger cell you can generate, but by coin cell, you can just generate by brush paint and by pressing. Okay, you can press it to make pellet, and then you can sinter that pellet to make it very strong or tough or high tensile and compressive strength, so it doesn't break. And then you can paintbrush to get either cathode or electrolyte or anode, vice versa, depending on whether you want to have electrolyte supported cell, anode supported cell, or cathode supported cell. And kind of power density with a nickel GDC, which is with the GDC I'm showing is low temperature fuel cells of 600 degrees Celsius, because 800 degrees Celsius you have to go to that high temperature, and the material becomes more difficult to develop, like interconnects. But at 600 degrees Celsius, you can really simply use a stainless steel as your interconnect, or steel as your interconnect. So these are some of the process that we develop. The cell testings. There's a button cell which we put it here, and then we have a connection, we have a hydrogen oxide going in and coming out, air going in, coming out, both for the, this is for the anode side, this is for the cathode side, and then this is actual figure which goes into our furnace where we initially required to heat it, but then after some time we have to stop it because it is exothermic reaction. We developed some new material, a lot of work we have done, but I don't want to go to the details of the research that we have done. You can get in our, we have almost like published 30-40 papers on Srfc alone. Okay, and you can see that different kind of material that we developed. Now, our emphasis was always on using a hydrocarbon as a fuel. So our anode development on perovskite material, lanthanum, strontium, calcium, titanate is the new paper that has come up in Electrochemical Society, ionics, solid state ionics, and things like that. And we do tests, and then we do some impedance analysis. This is resistance or conductivity analysis, half cell tests, full cell test. So all these analysis we do. This is our own cell. Anode, electrolyte, and cathode is shown you here. Thin layer of electrolyte, anode, and cathode. And what we get at intermediate temperature, we can go up to 400 milliwatt per centimeter square at about say 600 or 700 degrees Celsius. So I end here. Just last few slides were on the work that we have done long time back. Some recent work I did not discuss here because this is a kind of FDP program, sort of an introduction to solid oxide fuel cell. And if I give you too much of material to be covered, then obviously it will be difficult for you to get everything in one day. So I would now like to have an introduction because it should not be one-sided. And I just unshared my slide, and so that we could have some question answer session, whether one-to-one or the person who is coordinating the session can read out the question and then I can answer them. That will be a good way to learn. If anything that I have mentioned you have not understood, I can put back the slide again, which we want the slide to be back. But I would like to have some introduction and some question answer, because that is a great way to learn. I mean, you must be knowing, I mean, all of you must be teacher, some of you must be student, but the learning is, one is by reading books, listening seminar or workshop, a conference like what we are doing currently, and other one is to have interaction or interactive mode by in the form of a discussion, I would say. We can learn each other. So can we have some questions and discussion, please? Anybody, have any question?
Hello, sir.
Yes.
Thanks for the question. Just I want to ask how this Srfc from solid oxide based on solid oxide fuel cell.
Right.
Is there any difficulties creating Srfc based on the SOFC?
What difficulties are you in general telling in general difficulties, or you have some specific thing in mind?
No, I'm asking about general difficulties.
General difficulty, if you are starting this research, one is that getting all the material. So there are companies in India, there are companies in Singapore who can supply, like Tosho can give you ISZ, interested in zirconia. Sigma Aldrich can give you all the material. So it is important to have some funding and get the material. although they're cheap, they're not very highly costly. Like other fuel cell requires platinum and other material, DuPont electrolyte, the proton exchange membrane, or what is popularly known as an Nephron membrane. All those are very costly. Compared to that, these are ceramic material, but most of the providers are from abroad. I mean, some Singapore, some Europe, some US, but available in India. So that's the first part you need to solve. You have to have some funding and you have to buy them. Once you buy the material, you need to have a tape caster. You need to have a press machine, at least 30 ton, so that you can pelletize and make the pellet, which will give you the strength, at least one of them, like anode supported or cathode supported or electrolyte supported, onto which you possibly can paint the electrodes that you want to make. At least one, it could be the bilayer cell you have to make by pressing anode and electrolyte or cathode electrolyte. The other can be like pen brush. If you are working on anode, particularly develop anode or develop cathode. The most problem that you're going to face is you can follow, of course, a lot of paper. They give a lot of recipe to make this paste out of anode material, cathode material, electrolyte material with a porous pore former, which could be glycerol, then a binder, which of course all get destroyed when you heat it, but later, but at this point you need to do that, and water, so that you make a right consistency in the viscosity and surface tension, so that you can laminate. So you put a doctor's knife and you can put a thin layer on a glass. Now here, once you do that and you make these 3 layers, often you will see there will be a buckling when you do the centering process, because once you have done it at room temperature, then you need to center it about 1000, 1200, 1300 degrees Celsius, so that all those material get adhered, the structure is formed, and there's no change in the structure when you operate the cell at 800 degrees Celsius. So if you sintered at 1300 degrees Celsius, whatever cubic structure of YSG is there, just formed, there will be not much deformation will take place, so you can operate the cell. The problem now comes once you have laminated, tape casted, or you have used a press machine to make the pellet. You have to have a right formula so that there is no buckling, there is no delamination. Buckling means it should remain straight, it should not become like this. And delamination means you have 2 layers and it should not become like that. So that's when 2 layers will remain 2 layers like this. You started with that at room temperature, made 2 layers. When you center it at 1200 degrees Celsius, then it remains like this and becomes hard. And it will not break, but it should not delaminate like this. So that is the hardest part of the first step in SFC, R&D or research. Once this is possible to solve, there are many papers, if you almost follow them in the experimental method, you will get it, not in first shot, but in 5th attempt or 10th attempt, you will get it, because they will be not mention everything. Maybe small thing they might have missed or not thought not so important. There's nothing to hide here. I'm just saying, maybe it is very obvious for the person who is writing the paper, but may not be so obvious for who are following the paper and doing the things. So that is the toughest part. Once you have managed to make the thin film, centering it, which is not delaminating, as you understand what I mean by delamination, then you are done. Then you have to make the connection at the top and the bottom with the silver wire, silver paste, and put it in the cell, and then increase the temperature, measure conductivity, measure voltage or current, galvanostatic or potentiostatic mode. I think some little bit of electrochemistry or your exposure to electrochemistry must be there, so that you understand those potentiostatic measurement, galvanostatic measurement, ohmic resistance measurement, conductivity measurement, impedance spectroscopy, or impedance analysis. I think these all must be part of the FDP program. So those things obviously you need to. And then obviously you need to supply hydrogen, oxygen. That, I mean, that I did not mention. So those arrangements need to be made.
Okay, sir. Thank you. And I want to ask one more question. What is the current status of reversible SOFC?
I think your question, you said that current status of reversible SOFC, correct?
Yeah. So we can use for both the electrolyzer mode and the fuel cell mode.
Yes, yes. So SOFCs are absolutely, there is no, like, if we use PEM fuel cell with platinum, that is completely reversible. We call it unitized regenerative fuel cells. In SOFC and SOAC is also same. I mean, there is no, but if you are using hydrogen oxygen based SOFC, which is nickel Cermet or nickel YSC as the anode, YSC as electrolyte, and LSM or LSCM as the cathode, then it is completely reversible. I mean, we have our own cell tested that we sometimes plot, I'm not sure here, and SOFC and SOEC mode on the same cell, and it perfectly works. I mean, in part, some part, I think those who are understanding or not, in some part, it is you are providing hydrogen, oxygen, and it is creating a potential difference, and you are putting a resistance, and you are able to measure the current. So then you get an IV curve, right? So in that part, and once you reverse the role, you actually provide water and you apply potential, okay, and then hydrogen oxygen comes out. That's the SOEC, solid oxide electrolyzer cell. That is what this questionnaire came. I'm explaining it. Those who are attending it, they don't know. So I'm actually giving water to my electrode, and it is splitting into oxide ion and hydrogen. So oxide ion goes to other side, takes electrons to produce oxygen, just a reverse reaction of the fuel cell reaction that I showed, to make hydrogen oxygen out of water. And then you have to apply, of course, potential difference to give that electron. So then this opposite reaction of hydrogen oxidation and oxygen reduction will take place, which is like water will split into oxide ion and hydrogen, and oxide ion then gives takes electron to gives oxygen. It perfectly works. I mean, this we have done, and you repeat it n number of times. There is no degradation as long as you are working off pure hydrogen, pure oxygen, YSC as electrolyte, and nickel Cermet as anode, and LSM or LSGM as cathode. And electrolyzer is also a very important aspect of the technology of hydrogen energy, that you also want to make hydrogen, because not available in nature, which is in the case of fossil fuel, almost available in nature, which can be utilized. Well, although we do some refining to get many other products out of it, but some of the fossil fuel, like gasoline or the crude, is available in such a form, can be immediately can be used, especially in Saudi Arabia and Iraq, having very low content of heavy hydrocarbon. But hydrogen is not like that. So you have to make hydrogen. Either you split water by using photon to make hydrogen oxygen, or you use photoelectrochemical, both photon and electrical potential to split water to make hydrogen oxygen, or you completely apply potential coming from photovoltaic, okay, and split water to make hydrogen oxygen. So that is important in this case of the technology. So SOEC can play a very good role in terms of if you have a heat which is available, let's say thermal nuclear power plant, a lot of excess heat is generated. A lot of heat is generated in nuclear power plant when you have the fission reaction going on, and heat is actually have to be taken out. So that waste heat can be utilized to do steam electrolysis in SOEC very effectively. because you require energy in this case, in the case of SOEC. And so because in this case, of course, it is an endothermic process, you require to supply heat and also electrical energy, so that you can operate at 800 degrees Celsius to split water to make hydrogen oxygen. Of course, you get some of thermal energy by applying potential difference. When you apply, you know that if you apply potential difference, then you have a heating of the conductor take place. So that kind of thing also will be there. Some amount of joule heating will be there, but mostly you require to supply heat for splitting of water. So you say that heat can come from the nuclear power plant, where you have a lot of waste heat. So BRC has developed SOEC based on this. All other countries also developed because of the availability of waste heat. The best utilization is to make hydrogen and store chemical energy in the form of hydrogen, and then utilize it in fuel cell.
Is there any performance reduction compared to separate electrolyzer and fuel cell in this reversible SOFC?
I just again repeat myself the question so that I understand. You are saying that when you are operating a SOFC and SOEC in dual mode, is there any performance reduction in SOEC? Is it the question, or only SOEC is the question?
Yeah, in compared to SOFC, is there any performance reduction if you use like a both mode, dual mode?
No. Perfectly fine. You feel, as long as, because even in PEM fuel cell, I'm just always compare with the PEM fuel cell. In PEM fuel cell operating at about 70-80 degrees Celsius, you really require pure hydrogen and pure oxygen. You must have been told by this time. Otherwise, it will, if there is some amount of hydrogen having carbon monoxide, it will poison the platinum catalyst. In this case, it is because you are operating at 800 degrees Celsius, you do not have platinum. Of course, you have all ceramic material and metal, nickel and transition metal oxides as anode cathode. So at that high temperature, even your hydrogen have a little bit of CO, doesn't matter at all. It all gets burned by the sheer high temperature that you are operating. So the degradation of SOFC and SOEC, even the fuel is not pure, the water is not pure. In the case of PEM water electrolyzer, your water need to be really pure. Otherwise, it will again degrade the anode, cathode, and electrolyte. But if the water is not pure, I'm not saying exactly the sea water. If the water is not pure, doesn't matter at all in the case of SOEC. And if the hydrogen is also not pure, having a certain amount of carbon, like carbon monoxide, it also doesn't matter, because it will just come out. It will get burned and come out. It will not, nothing would happen. Small amount. Okay. So the degradation is really not a problem in SOFC. The problem of SOFC is the interconnect. Interconnect it has to be electronic conductor, and it's a metal alloy or a steel or a copper steel, which can withstand that high temperature. It doesn't get melt. That's what I mean. So a special APU 22 steel is required, interconnect. So that's costly, and then there is a leakage from the sides, and so the sealants need to be replaced time and often. I'm talking about when you're talking about working for 30, 40, 50,000 hours. Okay, so that is a problem. Those problems are not arising in PEM because you're operating at 800 degrees, 80 degrees Celsius, 90 degrees Celsius. But here operating at 800 degrees Celsius means you could lead a leakage problem. Interconnect is a problem, and that temperature interconnect can also get poisoned by, chromium dissolute or chromium incorporation in the interconnect, which is chromium steel, and then leading to some corrosion is a problem in SOFC. So these kind of problems are there in SOFC degradation.
Sir, you mean we don't need deionized water for electrolyzer?
Absolutely not required. Salt water might give a problem over a time. Salt water means I'm talking about direct seawater, not salt water, seawater. But deionized water is not required in SOEC operation.
Okay, sir. Thank you. Thank you so much for your presentation, sir.
Okay, thank you. Thank you very much.
Any other query from the audience, from the participants? Queries, any queries? Any more queries from the audience, participants? Please introduce yourself and then ask. Please introduce yourself and then ask. One by one, one by one, one by one.
Good morning, sir. I am Rajwala,
Yes.
MTech student at NIT Jamshedpur. Sir, my question is that, sir, I just want to work on electric vehicle in India. Sir, in India, lithium is not available as much as it is available in China. Sir, solid oxide fuel cell can be used in EV. So I just want, is there any chance that solid oxide fuel cell may be used in electric vehicle as temperature, as it operate at higher temperature? So what can be the way? Should I proceed in for the research work?
No, so I tell you very frankly, you are from an academic institute. You can work on solid oxide fuel cell, and there are a lot of problems need to be solved. You can find out from literature review. I encourage you to do that. But developing a solid oxide fuel cell by you and putting into the vehicle instead of lithium-ion battery is a big problem. Big problem in the sense it's a problem to be solved by not you alone, but a big company and many people together. It's not that so easy. But I must say, not today, at least 10, 15 years back, General Motors, and today also, they all developed solid oxide fuel cell for e-mobility, especially trucks, because trucks required a lot of power. And that power coming from PEM fuel cell is a big fuel cell. Coming from battery is even bigger size battery. So General Motors, you know that they had they also had the car in India, but right now they do not have, I guess. They've gone from India. So they developed APU, the auxiliary power unit for trucks, because trucks require a lot of auxiliary power. I'm not talking about air conditioning or headlights and all, because trucks also they multi-purpose use. No, they use hydraulics to take the material into the loading of the material, unloading of the material, the tilt the back portion of the truck. So they require hydraulics, a lot of power for the hydraulics, apart from the AC and all the other auxiliary power. So they did develop for big truck companies all APU, auxiliary power unit, out of SOFC, put it in the truck, big truck, like you see the huge truck in the highway in India, such kind of bigger truck, even bigger than that. The trucks in US or China or in other countries are very big, very big. So it is developed. But most of the car companies are not into SOFC use, although it can be used, but there are problems. So obviously your safety is a big issue in case of SOFC when you are driving a car 800 degrees Celsius, although your IC engine works at 1200, 1400 degrees Celsius when it burns your gasoline. Of course, all IC engines figured that out and developed it nicely, so you do not feel it, you do not feel unsafe. But SOFC also, it is possible and it's going to come, SOFC driven car. But I know personally that trucks and buses are being tried and trialed, and it is very much existing for use of SOFC. I hope I have able to.
Yes, sir. Thank you, sir. Sir, as a research work, and I have only 2 semesters left. Should I move or should I change my topic?
No, you continue. Don't change your topic. You have 2 semesters left. Whatever you have chosen, 2 semesters with pandemic, whatever you can do in 2 semesters, continue that. Don't change.
Thank you, sir. Thank you so much.
Any other queries?
Sir, good morning. I'm Dr. Kumar Gaurav, faculty from UPS Dehradun. Sir, comparing SOFC and PEMFC, cost economics is favorable in which case, sir?
Your question, because sometimes this listening is so. Your question, if I understand, you are saying that the cost economy vis-a-vis PEM fuel cell and SOFC. Is it so?
Yes, sir. Yes, sir.
Yeah. So the cost. There are 2 things. One is the cost has many components. One is your capital expenditure, other one is a operating expenditure, other cost is your safety. Everything together cost comes. Okay. So in this case, the PEM fuel cell is much more developed, accepted by people, especially the automobile companies, and safety features are better in PEM because operating about 100 degrees Celsius or just below 100 degrees Celsius. So the heat management is very easy, because it's not about the fuel cell stack and fuel cell. The other paraphernalia that you have to have a system, which is, we call it balance of plant, BOP. That means fuel cell is just a stack, but the cooling of the fuel cell, heating of the fuel cell, all fuel cells working together, whether giving you right voltage current the time you require when you're driving a car in the mobility, because it's your driving cycle, you are accelerating, decelerating, stopping. These are all very complicated, balance of plant. You're not working on a constant voltage and current, because constant voltage current is generally in the power sector, although there is a fluctuation there too, but not too fluctuation like it happens in a car, because moment you are decelerating, second moment you are accelerating, because your road in front of you saw nothing is there, so I must increase my speed. So all those things, problems are there. So that way, and the safety, and capital expenditure and the operating expenditure, capex, opex, that you understand. I think the cost for PEM fuel cell, the way the development took place, is lower. Economics is better than the solid oxide fuel cell. But for a long run, if you want to find out a alternative to a thermal power plant, to give power to a city, then solid oxide fuel cell is much ahead of PEM fuel cell in terms of gravimetric and volumetric power density. And when you are talking about megawatt range of power generation, then SFC is the way to move. And you have a constant load, possibly most of the time when you are giving power to the city within constant load, there is a little fluctuation, always happen, but not like in a car. So economics, PEM fuel cell, very good for low use, low end use, in a sense a car, or a backup power for a room or a hospital or a building. But for a huge power requirement for a city, the cost of SOFC will be cheaper than PEM fuel cell. Suppose I require 500 megawatt power, and I want to have power because environmental is the issue. I don't want to emit CO2 by burning coal to generate steam and run a turbine, rather than I generate hydrogen oxygen from water using photovoltaic, and then run a SFC and give power to my city, which has a requirement of 400 megawatt. Then SFC cost is much lower than PEM fuel cell, which is very difficult to do that, to get such kind of huge power. You understood the economics, no? One side economics is lower power You have a 500 watt, 1 kilowatt, 20 kilowatt, 100 kilowatt, fine. PEM fuel cell is a better economics. If you have a 200 megawatt, 600 megawatt, SFC has a better economics.
Okay, thank you, sir. Thank you.
Any other questions? Okay, thank you, sir,
Thank you.
for your wonderful basics about solid oxide fuel cells. In fact, it's very much informative, and we thank you for accepting our invitation to give this lecture. Once again, I thank you on behalf of NIT and our department. Thank you.
Thank you very much.
Thank you, sir. Thank you. Yes, sir. Yes, sir. Participants can join at 1:20 in the afternoon for the next speaker's presentation. We will